Hello, Chemistry 11 Honors. Today's lesson, we want to talk about the introduction to thermodynamics. Now, for this particular topic, it actually delves a little bit deeper into a topic we had talked about in regular Chemistry 11, which was chemical reactions. Now, back in Chemistry 11, you probably were exposed to the exo and endothermic reactions. I think in my notes here, if I scroll down, okay, we talked about endo and exothermic reactions when we talk about chemical reactions. And you were introduced to something called the delta H, okay, whether delta H is a positive, delta H is a negative, depending on whether or not it was exo or endothermic. And you were introduced to something called the system and the surroundings. Now, these set of notes were what I had given in regular Chem 11. So if you were in my class, you should have a copy of these notes. So today's lesson in AP Chem is an expansion of this idea of exo or endothermic reactions and the idea of delta H. Now, when one is talking about thermodynamics, the key thing that you're looking at is you're talking about the transfer of energy in a chemical reaction. So when we talk about thermodynamics, it's the transfer of energy during a reaction. Now, what is energy? And energy is the ability to do work. Now, whether in grade 9, grade 10, physics 11, we talked about two general categories of energy, where we have kinetic energy, which is the energy of motion. Okay, and kinetic energy is calculated by half mv squared, where m is equal to the mass in kilograms, v is velocity in meters per second. And the units is kilograms times meter squared over second squared, which is joules. Another type of energy that you should have been exposed to is potential energy, is the stored energy or the energy of position. And it's energy associated with the forces of attraction or repulsion between objects. So those are the two general types of energy that we normally talk about. Now, in a perfect system, what happens is the potential energy and kinetic energy is constant, because theoretically the potential energy converts directly into kinetic energy and vice versa. And this is the basis of law of conservation of energy, where it states energy cannot be gained or lost, only converted. Now, another thing that you should be aware of is the terminology that we use. So when we talk about thermodynamics, we talk about a system, which is portion of the universe subject to study, specifically the energy in the bonds, in the reactants or products. So when we're looking at the bond energy and what's happening to the energy in the actual reaction, that is generally called the system. Surroundings is the portion of the universe in which the system interacts. Basically, what we can sense or feel as the reaction proceeds. So if we feel that something is hot, that is the surroundings. Now, when you talk about the two, you have your systems and your surroundings. You have the interaction between matter. So sometimes you produce things and it gets released into the environment, or you have energy exchanged. And we're going to be focusing on the energy exchange in this particular topic. Now, if we were to take the entire system and the surroundings, and we take a look at all of the matter or energy exchange, this is what we call the universe. So when we talk about the universe, we talk about the system and the surroundings and how it interacts with each other. and we've used that term before. It says the universe subject to study, okay? Or the universe with which the system interacts, portion of the universe. Okay, so I use that term universe. Now, the interaction, when we talk about interaction, is the transfer of energy or matter. Okay? Interaction is the transfer of energy or matter between the system and the surroundings. Now, we're focusing more on energy. So there are generally two types of energy transfer. We have work and heat. Work is the general energy transferred, while heat is specifically energy transferred from a hotter object to a colder one. So that is the difference between the two. One is a general energy transfer, we call that work. The other one is specifically transferring from a hotter object to a colder one. Now, another terminology you should be aware of is internal energy, is the total energy, kinetic and potential, within a system without any interactions with the surroundings. Okay, so if everything is perfectly isolated and there was no interaction between the system and the surroundings, within the system, we call that internal energy. And if there is no internal energy interaction with the surroundings, then the internal energy of a system is constant. All right. And it's called the first law of thermodynamics. So if there is no interaction, no heat or energy lost or gained between the system and the surroundings, what happens is we say that the energy is constant. Now, but because there's always interaction, it is impossible to determine the energy of a system. Therefore, the only way to determine the energy is to determine the change in energy. The key word is change in energy of a system as a reaction proceeds. So what we do is, because there's always going to be heat lost, heat gained, energy lost, energy gained, it's impossible to determine the final energy in a system. So we look at the change in energy. And how is the change in energy determined? Is the energy of the final state minus the energy in the initial state. When we talk about state, it could be things like the phases, whether going from gas to liquid to solid. Now, one final thing for you to be aware of: when determining the change in energy, it is considered a state function, where the state of the system determines the energy and not how it got there. Now, what do I mean by this? Is, let's say we had a chemical reaction, whether, let's say we had water as a gas, let's say goes to water, water liquid going to water as a gas. Now, there's a specific amount of energy here, and there's a specific amount of energy in the gas phase. Now, when we're talking about change in energy, all we care about is from this state to this state. We don't care if the water became like H2 plus O2, and then it went to HO and HO, and then finally to this. All we care about is from the start. All we care about is the start to the finish, when we don't care how we got there. The example would be like, for some of you, is your parents might want you to become, I don't know, a graphic design artist or a dentist, or they want you to go to university. They don't care how you go to university or what university you go to. All they want you to do is go to university. That would be like a state function. They just want you to get there from high school. Okay, So whether you apply directly or you go through colleges or technical college before you go to university and get your degree, all your parents want to do is get a degree. Okay, that's the idea of state function. Now, if you take a look in your textbooks, and let me see if I can get this up here. Okay, if you take a look on page 242 in your Zoom doll text, what you see is they break it down into a little bit more detail. So my suggestion would be for you to go through it and make sure that you do understand what they're talking about from pages 242 down all the way to 245, 246. If you look at the bottom of page 243, notice they use the term system and surroundings. And they elaborate it a little bit more. Okay. And if you go down, if you keep on going down, they even show you a picture of an exothermic reaction and an endothermic reaction. And you will notice this formula here. The change in energy is equal to Q plus W. What is Q? Q is heat. And what is W? W is work. So if you take a look on the bottom of page 244, top of page 245, they give you some examples. Okay. Bottom of page 245. And then if you take a look on page 246, they actually give you a little introduction, a little simple equation, a sample calculation for you to calculate how much energy is changed in a chemical reaction. All right, folks, thank you very much. Have a good day. Bye-bye.